Hey, folks, we're going to start talking about the last unit in mechanics, which is universal gravitation. And this is one of my favorite units for mechanics, basically because of the history of it. So let me start with that. I'll start with Newton's universal law of gravity. Okay, and then we'll talk a little history. So first of all, his equation, or the equation that we know now, looks like this. Force of gravity equals, now in the previous course you might have learned this. G m1 m2 over r squared. G being the constant of gravity, which is approximately equal to 6.67 times 10 to the negative 11th, and the units would be newtons meters squared over kilograms squared. Okay. So this is what the physics one equation will look like. The physics C equation, we've got a little extra to add in there. It's a vector, so you got to put a vector over that, and it's in the r hat direction, meaning radial direction. I'll explain that in a second. And it's inward, so we put a negative in front of this. So that just gives the equation. Now it's a vector equation. It has a direction to it. Okay, and that's going to be important later on in the chapter here. Okay. Now, the history of this. Okay, so I do have a little story to tell, and I'm going to spend a minute or two on that, and then we'll actually do some examples. So historically, the Greeks, the Egyptians, the Chinese, many cultures studied the heavens, and for a long, long time, most cultures thought that the sun went around the earth. And Aristotle was one of the first to write this down and record it. Ptolemy was basically backed him up with a model of the heavens, which I won't go into a lot of detail with. But what ended up happening is by the time you get to Ptolemy, it gets harder and harder to explain actual observations with the model of the sun going around the earth. It just gets more and more difficult to try to explain away some discrepancies in data. And there's a lot of detail with that I'm skipping over. But let's just say when you don't have quite the right model and you keep trying to make it work, eventually it's going to stop working. That's where we get to Copernicus. So if you look at the date here, you got these folks right around, zero, so, 2nd century AD, and then all of a sudden it's like 1300 years before you get Copernicus. So there's not a lot of science that happened in between there as far as the study of the heavens goes. But anyway, you got Copernicus, and he was the first to figure out that these folks here were wrong. And let me correct that. He wasn't the first to figure it out, but he was the first to mathematically demonstrate and write down why the Earth goes around the sun, and showing data to back up that assertion that the Earth actually goes around the sun and not the reverse of that. Now, the story is that Copernicus, he didn't actually publish this until he was on his deathbed because he was afraid of being persecuted by the church at the time. And at the time, the Catholic Church had adopted the Greek worldview that the sun went around the earth and the earth was the center of everything. And so if you spoke against that, that was not good. So Copernicus waited, according to the story, Copernicus waited till he was literally on his deathbed to publish his model. Then you have Galileo Galilei. And Galileo was he made a lot of observations that backed up Copernicus. So, for instance, phases of Venus he saw, which can only really be explained if both Venus and the Earth are going around the sun. He looked at the moon and saw, craters. So that was one other thing about the Greek worldview, that the things in the heavens are perfect. They're perfectly smooth. They go in perfect circles. Well, Galileo's seen bumps on the moon and mountains on the moon, right? Craters. Galileo also was the first to observe sunspots with a telescope, and that's part of the reason why he might have gone blind the last several years of his life. But the biggest thing, one of the bigger things that Galileo discovered was that the moons of Jupiter. And what he figured out was there are 4 moons that are easily visible with a simple telescope, even a good pair of binoculars. And these moons were clearly going around Jupiter, and they were not going around the Earth, which debunked the idea that everything goes around the Earth. Now, Galileo, having said all this, was then put under house arrest for saying it, and there's a long story behind that too. But he was what we call a Copernican. He agreed with Copernicus. You'll also see Tycho Brahe here, who's a contemporary of Galileo. He was an Aristotelian. He still believed that the sun went around the Earth. But what was good about him is he had a lot of money, and he was able to create this huge observatory, and he collected very, very precise data. Okay. Then you have Kepler, and Kepler worked with Tycho Brahe at his observatory. Kepler was a Copernican. Kepler eventually believed that the Earth actually did go around the sun. But Kepler went much farther, and I will talk about him in a subsequent video here. He came up with some laws of motion, one of them being that the Earth and the other planets are not going around the sun in perfect circles, but they're actually going in ellipses. And then you have Isaac Newton, who we're going to talk about now. And Newton developed laws of motion, and he also developed the law of universal gravitation. And what was special about this law, and I'll go back to the notes here, what was really special about this law was up until Newton's time, most scientists believed that the laws here on Earth and the laws in the heavens are different. And Newton was basically the first person to kind of show and demonstrate that, you know what, that's not quite right. This law of gravitation explains why both the moon circles the Earth and why an apple drops down toward the center of the Earth. It's the same law. The same law works both on Earth and in the heavens. Now, by the way, there's a long story behind this too, involving Halley's Comet and Halley. And if I have a chance in class to talk with you folks, I'll talk with you about the story about this equation and Edmund Halley asking Newton about Halley's Comet that he had sort of discovered. So there's a long story behind that too. But anyway, so Newton's law of gravitation is the first time that scientists really understood that the laws on Earth and in the heavens are actually the same. Okay. Now, this gravitational constant, Newton never actually came up with this value. This was gotten 100 or something years later by a person named Henry Cavendish, and he basically did experiments that measured the very small pull of two objects. Now, here's the idea. It turns out that any two objects pull on each other. So right now, if you have a pencil in your hand and a calculator nearby, that pencil is pulling on that calculator, and that calculator is pulling on that pencil. Any two things with mass pull on each other. Now, why that occurs? Scientists are still trying to figure that out. Matter of fact, Newton didn't know. Newton came up with this law, and he basically, when asked why it works, Newton basically said, I feign no hypothesis, meaning I don't know why it works, I just know that it does. Okay. So let's say this is M1, and let's say this is M2. Okay, maybe it's your pencil and your calculator. Well, M2 is going to pull on M1, and M1 is going to pull on M2, and guess what? Those two forces, by Newton's third law, have to be equal and opposite. Now, you may wonder, well, how can that be? Here's the Earth, and let's say here's me. Okay, so the Earth pulls on me, personally, with about 800 newtons of force. Does that mean that I pull up on the Earth with 800 newtons of force? You're darn straight I do, okay? The difference is what happens if we're separated and then I let us go. Okay, so here we are separated. So the Earth is pulling on me and I'm pulling on the Earth, and those two forces are equal and opposite. However, our accelerations will be vastly different. Mine will be about 9.8 meters per second toward the center of the Earth. The Earth will accelerate up toward me, but it will be a very, 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 very tiny fraction of that acceleration because the mass of the Earth is so much bigger than mine. Okay, so the Earth does actually accelerate toward me. It's just so tiny that we can never observe it. Okay, now, as far as using these equations in examples, on the next video I will actually talk about, we'll do some math with this equation, and then we'll derive an equation for the acceleration of gravity. But let me end the video with that. There are two things with gravity. We can't just say gravity. The answer to a question is not gravity. Okay, there's two things. There's the force of gravity. That's the pull of two objects on each other like this. And then there is the acceleration of gravity, little g, and that is how quickly one object accelerates toward the other due to that pull. So please, when we're talking in class about gravity, please not just say gravity. Okay, it's either the force of gravity or it's the acceleration of gravity. All right, in the next video, we'll do some numbers. Hope to see you then.